Okay, I'm going to talk about a kind of weird surface area problem. And it's of the following form. We're going to find the area of the surface which is created by intersecting two other surfaces. We're going to intersect the cylinder y squared plus z squared equals 1 with the cylinder x squared plus z squared equals 1. Which are two cylinders, and they go in different directions. And it's actually very hard to draw what's going on here. So we have one cylinder that extends in the x direction. So that's okay, but as soon as you try to draw that y cylinder, now things start to get a little bit cluttered. And it's not as clear what's going on. I mean, one way you can kind of get a sense to do is to draw it like with cross sections. For example, if I fix x, then what you do is you just plot y with z. So one of these cylinders will have a circle, but then another will just correspond to some kind of lines, if you look at the cross section. On the other hand, if you do it the other way, and for example, if you fix y, the colors would reverse, and we would see that black cylinder transposed against that red cross section. So you can sort of imagine the surface that's being made. It will look here, the cross sections of the surface will be what I'm shading. So it's kind of sphere-like. But it has 4 corners. So again, it's very hard to draw just something like this, but that's kind of the idea. The cross section of the surface will look like spheres. But how on earth do you get a handle on something like this? So the key insight you have to obtain is to look at the intersections between all of these surfaces. So recall that z squared appears twice. So you can actually subtract these equations, and you end up with y squared minus x squared equals 0. In other words, the intersections happen when y is plus or minus x. So this actually partitions the x and y into 4 regions. We might call this region 1, we could call this region 2, 3, and 4. And it's clear there's symmetry. Right, because these cylinders are all symmetric. So I would claim the surface area you can actually just do the surface area of region 1 times 4. So it suffices to look at the surface area in region 1. So why is this useful? To partition things based on these intersections. Well, it turns out the intersections serve as a switch. So the intersections, they switch on or off which cylinder is being used. So for example, in region 1, what we have is, it looks like y is less than x, and we also have y is greater than minus x. So in other words, y, the magnitude of y is smaller than x, and we also have x positive. That's what region 1 is. This is region 1. It's another way to describe it. And so if we go back to the equations, x squared plus z squared and y squared plus z squared, what actually happens here is only one of these equations will be our surface because, for example, if we do x equals 1/2 and y equals 0, so if we look at all these points, then it turns out the first one corresponds to 1/2 squared plus z squared equals 1, whereas the second one corresponds to 0 squared plus z squared equals 1. So this, if we use this equation, we would see that z is plus or minus 1. Whereas if we use this one, we would see z is 1 minus x squared. So in other words, this one now is a function, but this thing is just a line. So if we go back over here at our cross sections, this is that z equals 1 or minus 1. So this is not used. Whereas this is what we're looking for. We're looking for a function. So we see that the first equation corresponds to the function, whereas this one corresponds to the, how should we say, we should call it this, like the line. So therefore, we'll use this one. So the switch for region 1, it turned on the x squared plus z squared cylinder. So therefore, you can use x squared plus z squared equals 1 in place of our weird surface in region 1. And so this is the key simplification that we need in order to get a handle on this problem. We need something concrete, x squared plus z squared equals 1, and at the cost of restricting our domain. Okay, so now let's try to do this. So we rephrased the problem like this, using that switch. We're going to find the area of the surface x squared plus z squared equals 1 in the region, which I'll just sketch out. Okay, so you could go ahead with this, but I'm gonna do a trick. Let's just replace y with z, because I like y here better, and we'll put z here. So let me just write this down really quickly one more time, because the area doesn't change if we do if we do this trick. Area doesn't change, but I like having y as my second polar coordinate if we're looking at this as a cylinder. So now I want to do this problem. Let's find the area of the surface x squared plus y squared equals 1 in this region. And it should be emphasized that this is x positive. And I'm also going to draw that cylinder in the xy plane. And remember, x is positive, so I'm just going to draw that circle for positive x. And so if we would have extended y, we would have to draw a cylinder in that region, but I'm drawing the xy plane separately to make this hopefully clearer. So our surface is this. So here's the idea. We'll use the surface to get ds, and then we'll use the region to get the limits of integration. Okay, so we're sort of taking all the visualization out of this problem, and we're just sort of going about it mechanically because it's so difficult to visualize. But let's see if we can do this. So to get ds, we of course want good coordinates. In order to do our RU cross RV thing, because that thing is ds. So I'm going to just use polar coordinates because, and in fact we're in 3D, so this might also be called cylindrical coordinates. So the whole point is just let x equal cosine theta, y equals sine theta. So that means our r, that is our x, y, z, it's just cosine theta, sine theta, and z. It's a surface, so it's a function of two variables, theta and z. Okay, so we actually have experience with this. If we do r theta, this is just minus sine cosine 0. If we do rz, this should just be 0, 0, 1. Observe that r theta dot rz is 0. So therefore, if we do the cross product and take that length, it's just the product of the lengths. So that's easy. So therefore, ds is just d theta dz. Okay, so we have ds. So now we just need to get these limits of integration. So to get the limits, we're going to write the region in our coordinate system. So the region's characterized by two things. First, we have x greater than 0. And second, we have that z range. So z ranges from minus x to plus x. So now in coordinates, right, we're just kind of going mechanically about this. There's not a whole lot we can do. So these are the most natural things. So in our coordinate system, polar coordinates, let's go back to this xy diagram here. Our x, if we use theta, our theta is this angle, then our theta ranges from pi over 2 to negative pi over 2, clearly. So the first constraint corresponds to theta living in minus pi over 2 to plus pi over 2. So what about the second one? Well, there's not a whole lot we can do with z because it's polar coordinates. So just plug in what x is. X is minus cosine theta, and then z will cap out at plus cosine theta. Okay, so we have two variables and two limits. So that means we can set up a double integral. We can do a theta, we can do a z, and our integrand will just be 1 because we're getting the surface area, which is just the integral of ds. And our ds, remember, is 1 by this calculation here. So our z range, of course, is negative cosine theta to positive cosine theta, and our theta range is minus pi over 2 to pi over 2 by our mechanical polar coordinate swap. And this is a very straightforward integral to evaluate. I hope this was helpful. Thanks for watching.